So folks, the next topic after looking at cylinders that we want to look at is the topic of quadric surfaces. For most of you, quadric surfaces should be a new topic. However, there's no way we can study quadric surfaces without having a recollection of the conic sections that we studied in either pre-calculus or if you took calculus here as recently as calculus 2. But we need to do a quick review of those. So what is a conic section? A conic section is an equation sitting in R2 that can be written in the form ax squared plus bxy plus cy squared, etc. equals 0. And what we need is at least a, and I need to actually correct this, a, b, or c needs to be non-zero for this. Notice that what makes this thing what we call a conic section is the fact that each of these terms here has a degree of 2 or fewer. So this term has degree 2, this term has degree 2, this term has degree 1, this term has degree 0. Real quick, folks, we're calling this a term of degree 2. If I were to add up the degrees of all the variables in that term, that would have degree 2 as well. For simplicity, when we study conic sections, we usually assume b is 0. Otherwise, what we would have is a rotated conic section, so like a rotated ellipse in the xy plane, and we usually don't want to deal with those, so we'll just assume b is 0. So careful, a and c cannot both be 0, but if, So let's look at the case where if a and c are equal to one another and not both 0, then what type of object will we have? So if a is the same as c, then, and we're assuming b is 0 here, so if a is the same as c, then we would have a circle for this particular conic section. And let's go ahead and remind ourselves why. So here, for example, I've got a is equal to c. The x squared and the y squared have the same term there. Let's go ahead and see why this is a circle. So folks, I'm going to do a quick review of completing the square in order to do this problem. If you feel comfortable doing this problem, maybe just jump forward to the timestamp that I'll put up right here for you. Otherwise, I'm going to show you how to convert this into the traditional circle form as a matter of review, because it's something we'll be doing so often in this course. So the first thing I'd like to do is we're going to divide each one of these terms through by the coefficient of 7. So I'm left with x squared plus y squared minus 4x plus 6y is equal to 3. And then I'm going to collect together the x terms here. So we'd have x squared minus 4x, and I'm going to group those together, plus, and then we'd have y squared plus 6y, and I'll group together those two y terms, and then I'll take, if I had a constant term over here, I would take it over to the other side. So the next thing I do is I have to complete the square twice here. I'm going to complete the square on this part right here, and remember to do that, we take, here's the linear term, we're going to take half of that linear term, half of that linear term's coefficient, half of negative 4 is negative 2. So that's what we're going to take as our complete the square term. So we would have x squared minus 4x, and then I'm going to add to this inside of here plus negative 2 quantity squared inside that parentheses there. Now, and I better leave myself some room here, but over here we'll have 3. Now, we've just upset the balance of this equation by adding the complete the square term inside this parentheses. So we need to compensate by adding the same amount over to the other side. So over here, I'm going to go ahead and add the same value, negative 2 squared, or 4. Likewise, I'm now going to complete the square on this piece right here. And so my linear term is 6y. So the linear coefficient is just 6. And so the way we do this is we take half this linear coefficient, we square it, and then we adjust the equation as necessary to keep it all in balance. So this is what we'd have. We'd have y squared plus 6y, and then I'm going to add to that to complete the square term for this, which would be plus 3 squared. That's what I'm adding there. And so in order to keep everything balanced, because I've now offset the balance by adding an extra 9 on the left-hand side of the equation, I've got to keep that by adding a 9 over here. So now what do we have? If we go ahead and clean this up, the whole reason why we complete the square is because things now factor. So this factors to be x minus 2 quantity squared, and you could check that. If you FOIL that out, you'd have this line above it. plus y plus 3 quantity squared, and now that's equal to 16, and now this looks like the circle of radius 4 and a center at 2, negative 3. So we can go sketch this circle if we wanted to, and so let's do that quickly. If we go to the order pair 2, negative 3, out 2, down 3, there's our center, which isn't part of the graph, but I go ahead and draw it anyway. And then we could go ahead and sketch the circle. Oof, that's an ugly one, but we're just doing this roughly. And so we'll just say that that has radius 4. Okay, so the real point of doing this, though, was to recall the for the conic sections here. So if we have this conic section and B is 0 and A and C are equal to each other, then this conic section describes a circle. What about some other cases? Well, if A and C are not equal to 0, then we're either going to have an ellipse or we're going to have a hyperboloid, and it will depend on the product of A and C. If the product of A and C is positive, then what we're going to have is an ellipse. So here I've got a situation where we've got 4x squared plus 9y squared equals 36. So a lot of the values of the coefficients in the conic section would have to be 0 for that to be the case. And the question is what type of shape is it? So what do I expect you to take from this? I expect you to recognize this shape right here as an ellipse, just like I expect you to recognize this shape right here as a circle. And I just want to convince you that this is an ellipse. So what did you see in maybe previous courses? In previous courses, what you would do is you divide through by 36 to get a 1 on this side here. But we can go ahead and actually sketch this ellipse very roughly if we just go ahead and find its intercepts. So if we're in the xy plane here, if I let x be 0, and if I let x be 0 and I solve for y, I'd have 9y squared is equal to 36, or y squared is equal to 4, or y is equal to plus or minus 2. So when x is 0, we would have intercepts right here and here. So let's put tick marks on there. So there would be the two intercepts, 0, 2, and 0, negative 2. And if I did the same thing here to find the x-intercepts, I'm going to let y be 0. So I'd have 4x squared would equal 36, or x squared is equal to 9, or x is equal to plus or minus 3. So 1, 2, 3, there's another intercept. 1, 2, 3, there's another intercept. And you could do a quick sketch then to quickly see that this describes an ellipse. So again, when the A and C values are not the same, then we have an ellipse if their product is positive. So these could both be negative signs here. Of course, the first thing you do is divide them over. And anyway, you would end up with an ellipse. Okay? So we could do this one real quick here. I think I'll let you guys pause the video and sketch this ellipse. And by the way, if you're interested in some more detail, please click this link here. And what it will do is pull up some textbook information about ellipses. And let me pull that up here. Hopefully you can see that. And so if you want, in fact, these are the exact same two ellipses. So you'll notice this is the same one I was just working with if you divided everything through by 36. This is the second one that I'm asking you to look at if you divide everything through by 16. And so if you're interested in reminding yourself some more information about ellipses, here's a great page that would serve as reference for that. So pause the video and sketch this ellipse, and then I'll go ahead and put it up for you as well. So here are the intercepts to this ellipse, which I found the same way I described over here, and there's the sketch of that ellipse. Let me know if you have any questions on that. So of the conic sections, the one that you might have forgotten would be hyperbolas. And so hyperbola is again where you have that the A value is not equal to C, but in this case their product is negative. So here you can see, so if that's the case, what you would end up with is a hyperbola. And here you can see I've got this hyperbola right here. Here the A value is 5, the C value is negative 4, and their product is negative 20. So when that's the case, you're going to end up with some sort of hyperbola. I'm not going to do a full review of how to sketch hyperbolas, but know that as long as that, remember that b term that we assumed was 0, that bxy, as long as b equals 0, these hyperbolas will either be one of two types. Just like our ellipses were one of two types, our hyperbolas will either open up this way, or they will open up, oops, that should be smaller, or they will open up this way. So something like this. And sort of, although sketching hyperbolas is a useful skill, for what we need to do here, it's enough for you to decide which of these two types of hyperbolas is it that we're looking at. If you'd like more information about hyperbolas, go ahead and click the link, which pulls up the textbook information on sketching hyperbolas much more carefully than what I'm about to do. But all I'm going to do is decide which of these two scenarios am I looking at in this example here. So here we've got the hyperbola 5x squared minus 4y squared minus 80 equals 0. I'm going to first divide everything through by 80 to make this look like it'll look in the text. So if I divide through everything by 80, this would give me 1 over 6, or x squared over 16 minus y squared over 20, and this would give me a -1, and if I add that over, if you do that, then it'll look like the example in the text. And so since all I want to do is determine which of these two hyperbolas it is I'm looking at, let's think about this in terms of intercepts. So you actually don't have to write this out, but I'm going to do so anyway in terms of intercepts. To find the x-intercepts, we let y equal 0. And so if we do that, we would just have x squared over 16 equals 0, or we get x is equal to plus or minus 4. If we were to go to find y-intercepts, and this is what I mean by you could have determined this right off the bat, if you were to find the y-intercepts, you would let x equal 0, and you would solve for y, but that would be the equation minus y squared over 20 is equal to 1, but that's the equation y squared equals -20, and there are no real solutions to this because of the negative sign there. And so there are no y-intercepts. So in asking the question, which of these two hyperbolas are we looking at, I think we're done, because we know we're looking at this hyperbola here. But let's go ahead and quickly sketch it. So we found that the x-intercepts were at 4 and -4. So if we plot those, there's 4, there's -4, and we could go ahead and sketch this graph. And it would look something like this. Now what I'm not being careful about is actually what these asymptotic lines are here. And that's what you technically need to do when you give a nice graphical description of a hyperbola, and if you want a review of that, again, click that link there. But here we've determined the type of hyperbola that we're looking at. So that concludes our quick review of conic sections. The big thing that you need to be able to do, though, is when you're looking at an expression like this, or the other two expressions that we have, I need you to quickly be able to determine whether or not you're dealing with an ellipse, a circle, hyperbola, whatever, very quickly. And that's what we need to take from this section in our review of conic sections. We'll pick up now with the quadric surfaces in the next video.